In 2016, Samsung had a problem that turned a smartphone into a global safety crisis. The Galaxy Note 7 was supposed to be one of the company's most impressive phones. Instead, reports began appearing of phones overheating, catching fire, and in some cases causing property damage. Samsung stopped sales and announced a replacement program. The batteries would be changed. The problem, everyone hoped, had been found. But then something happened that made the story even worse. Some of the replacement phones caught fire too. The problem became so serious that regulators warned consumers to stop using the devices, airlines restricted them, and Samsung eventually recalled every remaining Note 7 and ended production. It was a spectacular reminder of something most of us rarely think about. A lithium-ion battery is not a box that simply fills with electricity. Inside that thin rectangle of cells is a chemical system that has to be watched, measured, and controlled. And that raises a surprisingly simple question. When you plug your phone into a power bank and leave it there for hours, how does the system actually know when enough is enough? Does the power bank know your phone has reached 100%? Does the cable somehow tell it? Or is something else inside your phone quietly making that decision? Because the answer reveals something most people never realize about the little battery sitting in their pocket. The power bank isn't actually in charge of your phone's battery. And to understand why, we first need to understand what that 100% on your screen really means. Let's get into it right here on Secrets of Simple Things. A battery doesn't fill like a bottle. The battery icon gives us a very convenient picture. At 20%, it looks mostly empty. At 80%, almost full. Reach 100% and it seems as if one final drop of electricity has filled the container to the top. A lithium-ion battery does not work like that. During charging, lithium ions move between materials inside the cell as part of an electrochemical process that stores energy. There is no physical line inside the battery marked full, and nothing is being poured into it as a fixed volume of electricity. Lithium-ion became so useful for portable electronics because it could store a large amount of energy in a relatively small, lightweight package. That combination made it ideal for laptops, mobile phones, cameras, and eventually the power banks we carry around today. The trade-off is that charging has to stay within carefully controlled limits. Electronics cannot wait for a battery to somehow feel full. They need things they can monitor: voltage, current, temperature, and the way those values change as charging continues. Those readings give the charging system a picture of what the battery is doing. Near the top, that picture starts to change. Why? Charging slows down. Near 100%. If a battery can accept a strong charging current at 30%, why not keep pushing the same amount all the way to 100%? Because the charging strategy changes as a lithium-ion cell approaches its upper voltage limit. Earlier in the process, the system can usually supply a relatively high controlled current while the cell voltage rises. This stage is commonly called constant current charging. It is one reason a depleted battery can gain charge relatively quickly. Then the system changes tactics. As the cell approaches its designed maximum voltage, around 4.2 volts for many traditional lithium-ion cells, the charger stops letting the voltage keep climbing. It holds the voltage near that limit while the current flowing into the battery begins to fall. The closer the battery gets to its charged state, the smaller that current becomes. Charging does not race into 100%. It eases into it. The system is not waiting for a screen to display 3 digits. It is watching for measurable conditions. The target voltage has been reached, and the charging current has fallen below a chosen threshold. Once those conditions are satisfied, the main charging process can end. So far, this sounds like the power bank has solved the problem. It has not. The more interesting question is whose charging circuit is actually making that decision. The power bank isn't the one in charge. In a typical USB power bank setup, the power bank does not decide when your phone's battery is full. The phone does. When you connect the two devices, you are really connecting two separate electrical systems. The power bank stores energy in its own cells, manages that stored energy, converts it into a usable output, and supplies regulated electrical power through the cable. Inside the phone, another set of electronics is doing a different job. Charging circuits, battery management controls, and sensors monitor the phone's battery and decide how much power it should accept at any moment. A simple analogy helps. Think of the power bank as a water supply. It makes water available, but the valve controlling how much enters the tank sits on the phone's side. That is the key division of responsibility. The power bank provides electrical power. The phone controls how that power is used to charge its own battery. As the phone approaches a charged state, its charging system reduces the current going into the cell. Once the required conditions have been reached, it can end the main charging process, even though the cable is still connected and power remains available. The cable never had to know the battery was full. The decision was being made inside the phone. The battery. The power bank is actually watching. If the phone is responsible for its own battery, what are all the electronics inside the power bank doing? They are watching another battery, the one inside the power bank itself. A modern power bank may contain a charging controller, voltage regulation circuitry, temperature monitoring, and protection against excessive current, excessive voltage, or short circuits. Together, these functions form the battery management system that keeps its own cells within intended operating limits while supplying power to another device. Even while supplying another device, those circuits continue watching the power bank's own electrical conditions in the background. Some designs use several lithium-ion cells instead of one. That adds another layer of responsibility. The cells have to stay within acceptable conditions together, and some designs also monitor or balance differences between them. This is why a power bank is more than a battery with a USB socket. Its electronics have to manage energy in two directions, charging the cells inside the unit and delivering usable power out to whatever is connected. What they are not doing in a typical setup is staring at the percentage on your phone. The power bank is responsible for its side of the cable. The phone is responsible for the battery on the other side. Now look at the number both devices like to show us: 100%. 100% is not a physical switch. When a display changes from 99% to 100%, nothing inside the battery suddenly clicks into a physical full position. The number is an estimate. Battery management electronics infer the battery's state from information such as voltage, current flow, charging history, and the expected behavior of the battery. The exact calculation varies by design, but the percentage is still a representation of battery state, not a literal gauge showing a container filled to its rim. Once the intended charging conditions are reached, the main charging current can be reduced or stopped. An indicator may change. A display may show 100%. Parts of the electronics may move into a lower power state. The battery itself does not become completely inactive. Lithium-ion cells naturally lose a small amount of charge over time, and the surrounding electronics consume tiny amounts of energy as well. Depending on the design, charging may resume later if the battery falls below the system's intended threshold. So 100% is better understood as a decision made from measurements. The system has reached the state it defines as charged, and the same idea applies to the power bank itself. What happens when the power bank reaches 100%? A power bank also has to be recharged, which means its own battery eventually reaches the top of its charging cycle. When that happens, its internal charging circuit uses the same basic logic we have already seen. It monitors the condition of its own cells, reduces the charging current as the target is approached, and can end the main charging process once the intended conditions are met. The lights may change. A small display may read 100%. The unit may move into a low power state. That does not mean every electron inside has stopped moving, or that the battery will remain at exactly the same state forever. Small losses continue, and the electronics themselves still consume a little energy. Depending on the design and battery management strategy, the system may check the battery again later and resume charging if needed. A power bank does know when to stop charging one battery very directly, its own. What it does not normally do is make that same decision for the battery hidden inside your phone. What happens when the numbers go wrong? Most charging happens inside a narrow operating range. The protection system becomes important when something moves outside it. If temperature rises beyond the expected range, the system can reduce charging power or stop the process. If voltage moves beyond its intended limit, protection circuitry can intervene before the cell is pushed farther. Current creates another kind of problem. An abnormal surge or a short circuit at the output can trigger the system to cut power and, in some designs, disconnect the battery from the output path. The electronics do not need to understand danger in a human sense. They only need to compare what they are seeing with limits defined by the design. Measurement, threshold, response. That simple pattern is doing a great deal of work inside a device most of us treat as nothing more than an emergency battery, and it brings us back to the phone sitting on the table. It doesn't know, it measures. The screen says 100%, the cable is still connected, the power bank is still sitting there. So why is the battery not being charged forever? Because the system never depended on one device noticing that the percentage had reached 100 and switching everything off. The phone controls how its own battery accepts power. The power bank manages the energy source on its side. Each reacts to the electrical conditions it is responsible for. What looks like a battery with a USB port is really a carefully controlled exchange between two devices, each making small adjustments as conditions change. That is the hidden engineering behind a moment that looks almost uneventful. The next time your phone reaches 100% while the cable is still attached, nothing mysterious has happened. The charging process has simply reached the limits it was designed to recognize. A power bank does not need to understand when enough is enough. It only needs to measure it. If you enjoy discovering the hidden engineering inside ordinary things, subscribe to Secrets of Simple Things for more stories about the simple objects we rarely stop to question.